Déjame entonces regresar un poco, revisar que estuvimos tomando el clase anterior. It's about the ocean surface as the cradle of life, la cuna de la vida. Because we know there are various different theories about where origin of life happened. Maybe some of you know that one of the most famous, or maybe the most accepted, is that life started at the bottom of hydrothermal vents, at the bottom of the ocean, or on thermal vents on the Earth's surface. And there are other theories that life started in some other planet outside of our solar system and was transported to Earth. But that, of course, does not explain the origin of life, because we would still have to try to explain it on another planet in maybe a different solar system, and how it got to the Earth and survived the journey to Earth through space. That theory was by Hoyle and Wickramasinghe, which are two people in England, which came up with the idea of panspermia. But to me, it makes much more sense to imagine that life started on the surface of Earth and in the oceans, and on the surface of the oceans, because the surface of the ocean would have been by far the greatest area available to the origin of life. And it would have been exposed to ultraviolet rays from the sun, which we are considering was the fundamental driver of the origin of life. So just to review very briefly what we said last day then, is that we had a hot Earth, so we had a lot of volcanism, and volcanism would have been giving these molecules, carbon dioxide, nitrogen, water, methane, and maybe some hydrogen. And we would have had this UV light at the surface, and the surface would have been hot, about 80 to 85 degrees centigrade, and that they know from the oxygen isotope ratios. And of course, more volcanoes, more hydrothermal vents, and probably more asteroids and comets who were arriving at Earth, maybe bringing some of the original material. But we don't have to assume that. We can assume that the material was in fact produced on the Earth's surface by the ultraviolet light through this dissipative structuring. And then I gave another slide showing that solar radiation within this range, about 230 to 280 nanometers, is by far the most available form of energy, or free energy, which was available on the Earth's surface compared to all the others. No, it's about 4 times 10 to the 4. Whereas, for example, with lightning, it's only about 1/10 or less than 1/10 of that energy in lightning, which would have been available. So there is a good argument that the solar radiation in the UV range, UVC range of 200, let's say 220 to about 285 nanometers, would have been how life got its energy, its free energy for formation. And it's also a continuous source. So these other sources like lightning, for example, or shocks from meteor impacts were only temporal. You know? So they came and they went. They were only instantaneous. But the solar radiation would have been continuous, at least for 8 hours a day. And then we had to wait for another 8 hours of night. And then again, we would have continuous radiation for 8 hours. And that is in fact what life needs. It needs some kind of continuity in being able to be a process which is dissipative, because a process which is dissipative needs a constant or almost constant free energy gradient over the system. Of course, the solar radiation, which has wavelengths of greater than 300 nanometers, would have been even greater component. But it turns out that this energy, the energy in the photons of this wavelength, are not enough to break and remake carbon double covalent bonds. So many of the molecules of the fundamental molecules of life, which have these double carbon covalent bonds, could not have been made with this radiation with wavelengths greater than 300 nanometers. So I gave you the hydrothermal vent origin of life postulate or hypothesis, and some of the positive features of this theory of the origin of life is that, well, we had these temperature gradients at the bottom of the oceans, because the ocean water is about 4 degrees centigrade, and the hot liquid coming out of these vents can be up to 500 degrees centigrade. So we have a very strong temperature gradient, and therefore we have free energy in the temperature gradient, which could have been used by life. We also have pH gradients. Okay, so that is like charge gradients, and that also is a source of free energy, which could have been used to produce life. And we supposedly have a lot of minerals which are coming out of the depths of the earth through these hydrothermal vents, which could have acted as catalysts. And another reason they give for being a positive region for production or the origin of life is that life would have been protected from the UVC light. Okay, but we're saying that this is not necessarily positive. In fact, it's probably negative. That life, the origin of life, needed this UVC light. So the negative points of this theory are that there's very little observed production of organics at these hydrothermal vents. And they have, in fact, tried to reproduce them in the laboratory. And even in laboratory conditions, they can get very few organics. I think they're only able to get some of the fatty acids, but they are not able to produce the nucleic acids, for instance, at these kinds of conditions with these high pressure and high temperature conditions. And in fact, today, the life that they find around these hydrothermal vents at the bottom of the ocean does not come from using the free energy of these vents. Some of it does, but most of it comes from the rain of organic material, which carries free energy with it from the surface. So the surface life which is using light, is dying, and some of it is raining down to the bottom of the ocean, where these animals are making use of the free energy, which eventually came from the sun. No? So at the beginning, they thought that all of the life around these hydrothermal vents was utilizing the energy from the hydrothermal vents, but now they're realizing that most of this life is using the free energy in the material which is raining down from the surface. And another reason, or negative reason, why this hydrothermal vent hypothesis of the origin of life is not considered to be very valid. And this was in fact a reason that Miller gave throughout his life. He argued against, Stanley Miller argued against the possibility of life forming at these hydrothermal vents. And his argument was that, well, every 10 million years, all the water of the oceans is circulated through these hydrothermal vents. So all the living material or all the organics would have had to go through these hydrothermal vents every 10 million years. And at these high temperatures, you destroy all of the molecules. So if you have to bring the molecules up to 400 or 500 degrees centigrade, all of them will destroy. So he called them actually regions of destruction of organic molecules, not regions of creation of organic molecules. So there was a big fight between those who viewed the hydrothermal vent or the origin of life as being the most likely scenario, and with Miller, who assumed that the components of life or the molecules of life were produced in the Earth's atmosphere through lightning or through ultraviolet light. And another negative point about this theory, hydrothermal vent origin of life, is that we know that photosynthesis, and this is not oxygenic photosynthesis, it's actually photosynthesis anoxygenic, which instead of being based on water as the electron donor, it's based on hydrogen sulfide. Okay, so that's H2S instead of H2O. That photosynthesis began about 100 to 200 million years after the origin of life. So they have that pretty well defined. And so it's very difficult to reconcile an oxygenic photosynthesis with an origin of life hypothesis at the bottom of the ocean where there would have been no light at all. And so that it came about very quickly is rather surprising if life really started at the bottom of the ocean. If it started on the surface, well, then would have had to deal with the light, and it could have been using that light and then eventually to make photosynthesis. And we also know that many of the fundamental molecules of life have this interesting property that they absorb very strongly UVC light, and they dissipate this light into heat. And so this then also argues for a surface origin of life. Now, it's interesting, and I will show you some of the controversy around this theory, because even now I'll mention something interesting, is the person who originated this hydrothermal vent origin of life hypothesis is named Michael Russell. And a few weeks ago, about a month ago, he contacted me. So out of the blue, no, I didn't solicit his contact. He, through another person who sent him my article, contacted me, and we started having a discussion. So he likes our origin of life theory based on the surface and UVC light, but he has a lot of issues with it, of course, because he is hypothesized he was the originator or the grandfather of the idea that life started at the bottom of the oceans. So I started to answer him, contestarlo, and now we have a record of emails. So I think it will be very interesting for you to read and to see. So maybe in the next, well, over the holidays, I'll pass you the list of emails with Michael Russell, who was the originator of this theory, and my answers to his questions and his doubts and concerns and things like that. So I think that will be very interesting for you to read. And it also gives me some kind of hope that others are taking this theory of the origin of life based on UVC light very seriously.
Oh,
So,
profesor. Oh,
yes.
espere. Oh, es que eso está bien padre. ¿No podrá invitarlo como a un debate en la clase? Porque, bueno, la clase es en línea, entonces, no sé, yo creo que estaría muy padre.
Invite Michael Russell to give a talk here.
Sí.
Well, I
Sí,
don't
para...
think he's now about 85 years old or something like that. And he's actually retired. He was working at NASA and I think the University of Illinois, I think in Chicago, I don't remember exactly. But I don't think it would be easy to get him. I might try it, okay? Might try it. But he's like a very famous person in the world, no? And it would be difficult for us to get him to speak to 3 or 4
Pero
people.
te mandó correos, ¿no? Tal
Yeah,
vez
we
sí.
could send him an email and see what he responds, no? But anyway, I'll send you his emails. Please don't make them public because he hasn't given me permission to make them public. But it would be interesting for you to read them first. And then maybe if we decide that it's something plausible that we could write an email inviting him, no? Or at least maybe asking him to give us one of his talks. No, we could do that. He must have a lot of talks on YouTube, which we could find and maybe see that talk. No? Okay, we'll think about that, but it would be difficult. Okay, so let's get back to the ocean surface then, where we believe the origin of life started. So it's very interesting that the surface layer very close to the air-water interface, that means about a thickness of 100 microns, has a very interesting characteristic. It is in that first 100 microns of the ocean surface in which we find a tremendous amount of organic materials. So 100 microns corresponds to about twice the width of a normal human hair. So you can imagine it's very close to the ocean surface. It's not very thick at all. And in this layer, we have these lipids and fatty acids, which have one part hydrophobic, and that's the part which sticks out of the water, and the other part hydrophilic, which sticks into the water. So for example, on the fatty acids they have an hydroxyl OH and an oxygen, and then they have this carbon chain, carbon with hydrogens, and those carbon with hydrogens don't have a dipole moment, and so they're hydrophobic, and that's what sticks out. And the part which has a dipole moment is the head, which has the OH and the O and the oxygen, and therefore that is hydrophilic, and that stays in the water. So in fact, these molecules are actually out of the water, they're not in the water, but there's only a few nanometers in length. So we have these hydrophilic, hydrophobic molecules, which are at the ocean surface. We also have a lot of, cyanobacteria and other kinds of life, and including other molecules, including, for example, DNA and RNA, which is freely floating, which seems to be the result of lysis. So photons destroying the nuclei or the prokaryote bacteria and having their DNA floating on the ocean surface. And in fact, many people are suspecting, and then there are also these viruses, which are floating on the ocean surface, which have their own DNA and their simple proteins. So even many people had suspected that maybe new viruses are coming from this ocean layer. As we go a little bit further down, deeper, about 10 microns here now, we get into this bacterial neutron, which are small particles. They're living particles, but they're also abiotic particles in this area. And then as we get down to about 100 microns, then we have this fine phytoneuston, which is like small animals which are living off these bacteria. So, and the density here at the ocean surface is from about 10 to the 2 to 10 to the 4 times the density of this organic material a little bit deeper in the ocean. So we have increases about 10 to the 2, 10 to the 4 of the ocean surface, basically from a number of effects, which I'll explain in a minute. So we have these aliphatic molecules, which have one part which is hydrophilic and the other part, the tail, which is hydrophobic. And we also have bubbles from raindrops, for example, or from ocean waves, which go down into the water and then rise to the surface again. And when they rise to the surface, they carry with them organic material that they have found deeper below. And we also have this land-weir effect, which is effect of air or winds moving across the ocean surface and causing these little eddy currents. These eddy currents are also bringing then organic material to the surface. So we have basically these three effects which increase the amount of organic material at the surface. We also know that light, for example, in the short wavelength range is very strongly absorbed. Okay, so below about 100 nanometers, which in fact we don't have any light arriving at the ocean surface, but this is very strongly absorbed by water. But when we get down to about 300 nanometers, or here this is a 200 nanometers, which corresponds to the blue. So therefore, we get very little absorption of blue light compared to the other colors in the visible spectrum. And that is why blue light can be scattered more, and that's why we see the ocean as being blue, because the blue light is being scattered and not absorbed. The other colors of the spectrum are being more absorbed. Then when we get to the infrared region here, we get again strong absorption of infrared light due to the vibrational modes of the water molecules. So we have this narrow region, which let's say is from about 200 nanometers to about, well, maybe 1,000 nanometers, in which very little light is being absorbed by the ocean. So this light can penetrate deeper into the ocean. In fact, it can go down to about 100 or 200 meters of ocean depth, depending on the density of the organic material. But what I'd like to point out then is the organic material plays the part of absorbing where water does not absorb. So organic material has been evolved to absorb in the range of about 200 nanometers to about 700 or 800 nanometers, precisely the region where water is not absorbing very well. So if we look at the physical processes which are occurring on the ocean surface, and here I plotted the depth of the ocean. This is on the left axis. The depth as a function of, well, this is the distance along the ocean, or the ocean, this is the ocean bottom, and this is the surface. We see that basically all of the physical processes are occurring within about 10 to the minus 6 meters, which is a micron. So 10 to the minus 4 would be 100 microns, which is the layer in which the organic material is very dense. So we have these aliphatic molecules which are floating on the ocean surface, and then here we have the other organic molecules slightly below that. So for example, the diffusion of gas comes within this 100 micron limit, and we have heat conduction also within this range, and molecular friction. Well, so this is the region which is rather stable because there's a lot of organic material, so it has larger viscosity. And so we get very little turbulence until we go down to lower regions. So this in fact region is very stable region. And even though there are waves and there are winds which are breaking up this organic material on the surface, it recombines very quickly. So you don't lose this region of high density organic material. And most of the infrared radiation which is emitted is also within about 1 micron, comes from within about 1 micron of the ocean surface. The energy absorbed due to the light which is incident goes down, as I mentioned, to about 100 meters, which is about here 10 to the 2 here meters. But about 30% is absorbed in the first centimeter. And that's basically due to the infrared light, which is strongly absorbed by water. Now, it's also interesting that the ocean surface temperature also varies between night and day. So this is a profile of the ocean surface temperature as a function of depth. Here we have a depth of 10 meters, and about at 10 meters, the ocean temperature doesn't change during day and night, so it's constant. But at night, because of the evaporation which is occurring on the ocean surface, the temperature drops. So there's a drop in a few tenths of a degree on the ocean surface. And this is within 100 microns. During the day, okay, so this is at night, and this is the profile of the ocean surface temperature during the day. During the day, the ocean surface can increase from about 1 to 5 degrees Kelvin, again, depending on the amount of organic material at the ocean surface. And so at this depth of about 0.1 millimeters, which corresponds to 100 microns, we get the maximum increase of about 5 degrees Kelvin So we get this variation from day to night of the ocean surface temperature, which was useful in our UV tar mechanism for denaturing DNA, as I mentioned. So this is just another graph showing the amount of heat which is given off the ocean surface as a function of time during the day from 0 to 24 hours. So in the morning at 6 o'clock is when there's very little emission of heat from the ocean surface, because that is the ocean surface is coolest. And then at about 2 o'clock in the afternoon, or 14 hours here, 2 o'clock we get a maximum, because that corresponds, this is the maximum of heat which is being emitted from the ocean surface. It's a maximum because the temperature of the ocean surface is also maximum. This is just for two different regions, but basically it's the same. There's a little bit difference depending on the latitude, but it's from about 2 o'clock to about 4 o'clock in the afternoon is when the ocean surface temperature is warmest. And we also have a variation of the salinity of the ocean surface. That is the concentration of salt. And that is, again, maximum at about 3 o'clock, between 2 and 3 o'clock in the afternoon. And could anyone imagine, any one of you has any idea why we would have a maximum of salinity at about 2 or 3 o'clock on the ocean surface? Any ideas? No? Maybe some of you don't have your microphone on and I'm not hearing you. Okay.
Pues no sé, solo se me ocurre la temperatura, pero no sé si está más caluroso el día a las 2.
Okay, la temperatura is maximum. Temperature is maximum at between 2 and 3 o'clock. But why would that give us a greater concentration of salt? It has to do with the temperature being highest at that point. Porque la más alta la temperatura, la más evaporación tenemos, ¿no? Entonces el agua está evaporando, dejando el sal atrás. Okay, so here we have an indication that the salt concentration is increasing, becoming a maximum at about 3 o'clock in the afternoon. And the amount of salt is also important because that defines how DNA denatures. If there's a lot of salt, then it's more difficult to denature DNA because, you know, it has the negative charges on the backbone. And so with salt, for example, the sodium ions, which are positive, they will latch on and cause it to the net charge to go to 0, which would make it more difficult for denaturing. So that is also an important factor to take into account, that the concentration of salt changes. But you can see it doesn't change very much, you know, it changes much less than 1%. So as I mentioned, that has an effect, both the temperature and the amount of salt has an effect on this UV tar mechanism, which we are suggesting was the mechanism for replicating DNA at the origin of life on the ocean surface. Now, it's also interesting to look at the distribution of chlorophyll over all of Earth's surface, including the oceans. So where it's dark blue here, there's very little chlorophyll, and that corresponds to regions far away from the landmass. So these regions of landmass can provide nutrients which allow the cyanobacteria to propagate. And so in these regions, and where we have currents, which is bringing the nutrients to the cyanobacteria, we see that we have a lot of chlorophyll, of course, because of the increase in cyanobacteria. But in these very dark blue areas, we have very little chlorophyll. And in fact, it is the animals, the fishes and the whales, that are bringing the nutrients to allow that even some of the chlorophyll to exist at these regions which are far away from the land masses. Okay, and here on the land surface, we have a lot of chlorophyll, which are due to the land plants and the trees, and we have some desert regions. So just to summarize then, some of the advantages to assume that we have a dissipative origin of life at the ocean surface. So this theory of the origin of life being due to the dissipative structuring of these UVC pigments. Well, here we have the highest intensity of free energy available, which is this light in the UVC range. And it's a continuous source of free energy. We also have a region of very high organic material density, about 10 to the 4 times greater than the water just below it. And we also have this region which has a large viscosity, and so we have low diffusion. It has a large viscosity because it has a lot of heavy organic molecules in that region at the ocean surface. We also have this day and night temperature cycling of about 4 degrees centigrade to facilitate this UV tar process. And another important fact is that because of this life at the ocean surface, which is helping to increase the evaporation of water, because as I mentioned, life is absorbing between about 230 and about 285 nanometers, where water does not absorb light. And so life, by absorbing this light in this range, can increase the amount of evaporation, which, as I mentioned also, is coming from the upper 100 microns of the ocean surface. So therefore, life can couple very nicely to the water cycle. Okay, I'm going to now go to another talk, but if there's any questions, I'd be very grateful for any questions. If some of you would like to ask a question about the ocean surface as the cradle of life, la cuna de la vida.
¿Y hay algo que explique la otra teoría, la de que la vida nació en las profundidades del océano, que no explique esta teoría, que surgió más bien en la superficie?
Perdón, Esmeralda, ¿cuál es tu pregunta? De si esta teoría del origen de la vida en los ventos hidrotermales.
Sí. Sí, esa explica algo que esta otra no pueda, porque ahí está como lo positivo y lo negativo, ¿no? De esta.
Sí.
¿Y hay algo negativo? ¿Hay algún conflicto en esta teoría de la...
Bueno, para ellos, ¿no? Por ejemplo, esa es, yo creo que la más importante para ellos es que está protegido de la luz UVC. Porque hoy en día, si exponemos la vida, organismos, insectos o bacterias a esta luz UVC, sabemos que se mata rápidamente, ¿no? De hecho, utilizan luz del UVC para esterilizar el agua, ¿no? Tienen lámparas que puedes comprar. Te vas al centro de la Ciudad de México, puedes comprar una lámpara UVC para desinfectar tu agua. Porque esta luz hoy en día sí destruye la vida, se mata la vida. Y es porque principalmente las proteínas, ¿no? Que están doblados de una manera de tal que su estructura en 3 dimensiones define cómo se actúa. Pero con la luz ultravioleta puede fácilmente, si está absorbido en estas proteínas, que contiene algunos de los moléculas fundamentales como los aminoácidos aromáticos que absorben fuertemente de esta luz ultravioleta. Bueno, este calor que está depositado por absorción de esta luz puede destruir las proteínas o cambia su forma 3-dimensional, entonces ya no funciona. Y esta acaba con la vida muy rápidamente. Y entonces esa es la razón más frecuentemente se dan para suponer que la vida tuvo que empezar hacia el fondo de los mares. Todo esto empezó con Carl Sagan en los años 70, cuando él, creo que fue uno de los primeros, si no la primera, en mostrar que esta luz ultravioleta en la región de larga longitud onda, de UVC, sí estaba llegando a la superficie del planeta. Él fue uno de los primeros a mostrarlo y enfatizarlo. Entonces, él buscaba maneras en cual la luz pudiera ser protegida de esta luz. Hablando de maneras abióticas, por ejemplo, otros materiales que estaban flotando en la superficie del océano, que no permitían la luz ultravioleta llegar a la materia orgánica que estaba más abajo. Entonces buscaban muchas maneras para proteger la vida de esta luz en el UVC. Pero en realidad vemos que la superficie fue expuesta a la luz UVC por un tiempo de 1,000 millones de años. Entonces no puedes imaginar que la vida estaba o escondiendo de esta luz por tanto tiempo. Debería de haber adaptado por lo menos esta luz en el UVC. Y solo por esta razón se van al fondo del mar. Porque el resultado hoy en día es con estos experimentos en el laboratorio no se puede producir las moléculas fundamentales. Solo los ácidos grasos fatty So there's nothing that this hydrothermal vent hypothesis would add to what we could do at the surface. Only, for instance, when the life became so complex that it had many different molecules, complex molecules, proteins, which had to be protected from UV light. But we know that about 1,000 million years, we started to get, after the origin of life, we started to get oxygenic photosynthesis. And that oxygen went into the atmosphere after the saturation in the water, because you know that oxygen is a very strong oxidizer. So if there's any metals, for example, iron in the ocean, the oxygen will band with the iron and in fact form these banded iron formations. So it took a while to get all of the oxygen from the oceans to sink into these banded iron formations and to allow the oxygen to escape into the atmosphere. And once it was in the atmosphere, then through also action of ultraviolet light, it could form ozone. And ozone